opening talk, one of the questions he touched upon was the question of efficient proof search or automatability. And our next talk will deal, I think, specifically with this topic. So Robere from McGill will give us a survey about automatability.
Thanks, Jakob. And thanks to the organizers for inviting me to give this talk. So like he said, I'm going to give a survey about automatability, which is kind of the proof theory, the proof complexity way of analyzing proof search. Okay, so let's start off with the basic question. Automatability, what is it? So here's a picture of a SAT solver. So a SAT solver as input gets some CNF formula. And then we feed it into this nice algorithm A, and it's going to tell me if it's satisfiable or if it's not satisfiable, right? Easy peasy, done. Now, however, the SAT solver by itself is not only going to just tell us if it's SAT or not SAT, it's also going to provide some witness for these facts, right? So on the one hand, if it's actually satisfied, it's going to give us a satisfying assignment. In fact, that's usually the piece of information we're actually interested in finding. And if it's unsatisfiable, and if we've turned on proof logging or whatever, then it's going to return that it's unsatisfiable, and it will also certify this by giving a refutation of that formula, right? Like a proof that it's not true. And so the way that we can think about this is that if I just ignore the satisfiable case, I could take any tautology and negate it, and I'll get a contradiction. And now I can think about this SAT solver as a kind of automated theorem prover, if you like, right? If I run some contradiction through this, say the negation of a tautology, I run it through, well, it's going to spit out a proof that this thing is a contradiction, which is, of course, a proof that the original formula was a tautology. Does that make sense? Okay, great. So now, well, unfortunately, we're not in a world where these things run efficiently all the time. So in particular, this thing is not going to run efficiently no matter what on all inputs because, well, we broadly believe that P is different from NP. But in fact, the situation is a little bit worse, right? Because of the one-sided nature of NP, if I feed in an unsatisfiable formula, it's not even necessarily going to be able to output a short proof of this thing, right? So, and this is, I mean, the complexity theoretic way of saying this is that we believe that NP is different from co-NP, but this means that, well, I mean, one way to think about this in an applied setting is that the proof logging might be a lot more expensive than simply just than not doing that, right? And so, you know, there's lots and lots of examples. We saw some examples in Albert's talk, but for example, I mean, any resolution refutation, and resolution is kind of one of the systems that a lot of SAT solvers do their sort of reasoning in. There's a lot of stars to put on that statement, but bear with me. Any resolution refutation of the pigeonhole principle requires exponential size. So even if you plug these relatively simple formulas in, any proof it's going to output is going to necessarily be large. So an obvious question then is the following. Can we design a solver such that the length of the refutation that gets output is never far from optimal, like never far from the length of the shortest proof, right? It might take exponential time. In fact, it's going to have to sometimes, right? If we believe that NP is not equal to co-NP, which is, in my opinion, a believable assumption. But maybe we can still find a proof that's not too far from this exponential length optimum. Does that make sense? Okay. And that's exactly what the automatability question, is asking. So here's some notation. So if P is a proof system and I have some tautology phi, I'm going to use this S sub P of phi to denote the length of the shortest P proof of phi. Okay. And now I'll say that this proof system is T of S automatable by another proof system Q if there's an algorithm that, given any tautology as input, is going to output a Q proof of this formula in time bounded by the length of the shortest P proof of the formula. Okay. So in other words, this algorithm is going to give me, a tautology, and it's going to output a proof of that tautology, maybe in a different proof system. I don't really care. You know, like these SAT solvers that exist, they'll output DRAT proofs or something like that, not a resolution proof. But the important part is that the amount of time it's going to take is proportional to the length of the shortest proof of phi. Okay. So in particular, I'll say that this proof system is weakly automatable if it can be polynomial bound, like automatable up to a polynomial factor off of the length of the shortest proof by some proof system Q, like being very relaxed here. And I'll say it's even stronger. I'll say it's automatable if it actually gives me a P proof. Does that make sense? Any questions about this sort of definition? Okay, good. And now hopefully that we can agree that at least from sort of an like a theory of algorithms perspective, that this problem captures the proof search problem, right? As a theoretical algorithmic problem, right? So we're given a tautology, we want to actually find a proof of that thing, and we want to get some reasonable bound on the runtime of that proof. Okay, good. So now, related to the search version of this problem, I want to actually bring up another variant of this problem, which is like never really mentioned, but I think it's important to talk about it. And that's kind of the decision variant of this problem, which I'm going to, in honor of the meta complexity program that we're attending, I'll call MPSP for the minimum proof size problem. So what is this? Well, this is a decision problem now, and you're given a formula and some positive integer, and I'm going to ask if this formula has a P proof of length at most K. Okay, so this is a decision problem. The answer is either yes or no. Does that make sense? And so one can ask, okay, well, is this problem hard, right? Well, clearly it's in NP, right? If you give me a formula, I can just guess the proof and guess and check that it's less than length K, and then actually verify that it is a P proof by just checking. So it's obviously in NP. But the interesting thing about this problem is that it's actually known to be NP complete for many proof systems. And this has even been known all the way since the 90s. So for resolution, for instance, Iwama proved in 97 that it's NP complete to find such a thing. For these like stronger proof systems like Frege, extended Frege, polynomial calculus. In fact, this proof technique from this paper is very general. It applies to many different problems. We can already show that it's NP complete. So in some sense, proof search is hard, right? We already knew that in the 90s, right? So what's going on here? That's my first question for the audience. So these NP completeness results do not imply that automatability is NP hard. Why is that? Immediately. Why even study automatability? I already know that proof search is hard.
Why?
Why? Okay, why? Well, the answer is that if you go back to what automatability was saying, we're going to be automatable if I'm allowed to be off by the optimal proof length by a polynomial factor. But as is the usual thing in NP completeness, well, if all I need to show that this is NP complete is to differ between, say, K and K plus 1, right? Maybe finding that what this tells us is that maybe finding the difference between a proof of length K versus finding a proof of length K plus 1, that's NP complete. But it doesn't tell me anything about a polynomial factor off in approximability. Does that make sense? And I think that this is actually a reasonable thing. This actually motivates automatability as a thing to study because it's
you're saying it's like the difference between pinning down exactly whether it's a proof of length K, or whether there is a proof of any reasonable length. I don't care about the exact length.
Exactly right. Exactly right. Yeah. So this is good, and I wanted people to keep this in mind because we'll come back to this later. When we come back to this, so when we think about this polynomial approximation, we should just ask, okay, well, is it possible at all? Like the existing NP completeness results didn't rule it out. And the short answer to this question is that it depends. Okay. So on the positive side, well, for any proof system P, I can always find a proof in time. This is a very boring answer, 2 to the length of the proof. Why? Well, a proof is a bit string, and I can just brute force over all the bit strings and just check and see if the bit string that I saw in front of me is a proof, right? Okay, so that's an exponential time automating algorithm. It does actually give us something, at least. On the other hand, if I look at weaker proof systems, say resolution, it turns out that we can actually beat this runtime. You can actually do better than this 2 to the S to the P. And other notions of automatability, if we kind of relax it a little bit, like notions of degree or width automatability, this was kind of already alluded to, in Albert's talk, these turn out to be achievable actually quite efficiently in many senses. So in some sense, the positive side, the answer is yes. On the other hand, on the negative side, it turns out that getting polynomially bounded automatability is actually often NP hard. And this is true even for resolution, thanks to this beautiful work of Albert and Moritz-Müller. And the long answer, I guess, is the rest of this talk. So yeah. Any questions about this sort of so far? Cool. Okay, well, here's the proof system zoo. And I borrowed, by which I mean stole, this slide from Susanna, who's not here. So, oh, she is here. Oh, dang it. So here's the proof systems that I'll just be considering. This is far from a complete picture of all the proof systems that we've seen that people study and practice, but I think it's illuminating for automatability. So let's talk about both upper bounds and lower bounds, what's known in terms of automatability, okay? So in this picture, red is going to mean that we have no non-trivial upper bound for automating proofs in the system. Okay, so if I look at any of these red proof systems, the best algorithm that I really know of to get to automate a proof is just by doing this brute force checking bit by bit. Okay, the 2 to the s is the best we can hope for. For these blue systems, we can do something slightly better. We can use upper bounds from width and degree or other tricks. There's multiple ways to get these improved bounds, but we can use some non-trivial upper bounds in order to get something better. Okay, and for this very special case of tree-like resolution, there's a non-trivial algorithm, like a clever one, which we'll see later, that really doesn't use width or doesn't relax to these things. And here we get a better upper bound, and it turns out that this upper bound is tight, assuming some reasonable complexity theoretic conjectures. Okay, so on the other hand, if we contrast this to the lower bound side, so some of these colors have changed, I hope. Okay, good. Well, here it's kind of easiest to divide these things up in terms of the strengths of things, in terms of the strengths of assumptions. So up here for these very, very strong proof systems, if we assume things like cryptography, some standard assumptions in cryptography, then we can show that it's already, this might be small, but we can show it's already exponentially hard to even weakly automate these proof systems. Down on the bottom side, assuming NP is different from P, we can get lower bounds on automation, but we can't get any lower bounds on weak automation. And then we have this annoying middle slice of proof systems that I've drawn here where we can't really say anything at all. So we should think of the world as kind of like this. So on the high side of proof systems, once the proof systems become very, very rich, well, assuming cryptography, then we don't even get weak automatability. Once the proof systems are kind of weak, well, we can relax this assumption. And assuming P not equal NP, we will not get automatability. But this doesn't rule out the possibility that we could weakly automate it in some stronger proof system. And for tree-like resolution, we've almost completely understood what automatability is possible here. So like assuming ETH, we know exactly the runtime of the best algorithm, and we have that algorithm that achieves it.
The best thing is if and only.
Oh, yes, that's an if and only if, that's true. Yeah, thanks. This is definitely not. It would be super cool if you could turn this into an if and only if, but yeah, I don't know how to do that. Okay, so this was my bird's eye view. Are there any questions about this so far?
Sorry.
Yeah.
Just have a question. So for example, let's say in the world of SAT, we have some, it's an NP complete problem, but we have algorithms that can solve lots of practical instances, let's say.
Yeah.
Efficiency. And how does the situation look like for the minimum proof size problem? Do we have some?
Oh, that's a great question. Yeah, do people actually study this problem? I think that the algorithms that solve this problem are basically just like SAT solving. So like, I don't know if there's anything more geared specifically towards this. Is that your question?
Yes.
Yeah. I don't know of anything that's more geared to just solving this decision version, just trying to differentiate between their existing proof versus actually producing it in some sense, right? Like in some sense, if I'm trying to give an actual deterministic algorithm for solving this problem, a yes or no instance of this algorithm is going to be a certificate anyway. So it's kind of hard to escape proving things at the end of the day. Yeah.
Okay. I don't know enough about logic to really observe to, but anyway, where does extended, I've heard about something called extended resolution.
That's it.
Where does that fit in?
Yeah, that's extended Frege. That's the same as extended Frege. Yeah, extended resolution and extended Frege are the same.
I was just allowed to introduce a new lemma. That's what you meant.
Yeah, that's exactly right. Yeah. And that's on the picture back here. Sorry. It's all the way up here at the very top.
Way at the top, okay.
Yeah. Any other questions? Yeah.
So what is the crypto assumption?
I'll get into it a little bit. The answer is that it depends. The stronger the proof system is, the weaker assumption you need. So like for extended Frege, all you need is like maybe factoring is hard, or maybe even computing an RSA pair, like proving that that's secure. Once you get down to the weaker proof system, quote unquote proof systems, you need to make the crypto assumptions stronger in order to get them. But, yeah. But if you're happy with extended Frege, then you can just say factoring is hard.
There was another point that you raised earlier, which was just because there's no automatability for resolution, it doesn't necessarily mean you cannot have weak automation.
Yeah, absolutely true. Yeah, absolutely true. It's the whether or not resolution is weakly automatable is a great open problem. Yeah. Yeah. I think that this is actually a really nice problem in particular because these as I understand it, these SAT solvers that use DRAT and things like that, it's kind of like a weak automatability procedure in some sense because it's output, it's logging, it doesn't log a resolution proof. It kind of does the reasoning in resolution in some sense because it's branching on queries and doing unit propagation. We all know that those steps can be simulated by resolution. But when it logs the proof, it logs it as a DRAT proof, which is a very different system, a much stronger one. Right?
Well, except that they mostly just use RUP, which is a variant of resolution. And there's only very few steps that make use of the extension, the RAT.
Okay, cool, thanks. Okay, good. Good. I guess it does still use it though, which is still not.
Only pre-processing technique known as bounded variable addition, which basically inserts a new variable and refactors the clauses. And
Cool.
that's a very minor pre-processing step.
Okay, cool, thanks. Thanks for the clarification. Okay, great. So in the rest of the talk, what I want to do is I want to kind of show everyone both, went back too far. I want to show everybody both the upper bound side and the lower bound sides of these things. A lot of effort goes into the lower bound side, but I think the upper bound side is also worth kind of seeing what we can theoretically prove. So let's start by talking about upper bounds. And in particular, I'm going to focus on the case of resolution and tree-like resolution, as it's going to be a familiar proof system for everybody. So here's a slide that that's just for completeness. So let's define a resolution proof, just so that we're on the same page. So resolution, as we all know, it's a Hilbert-style deductive system. The lines are clauses, which are ors of literals. We're given two proof rules, the resolution rule and this weakening rule, where I can just add in some extra literals to a clause if I want it. You don't actually need this weakening rule. It's just handy to have it around sometimes when you're proving things. The length of the proof is the number of lines in it. The depth of the proof is going to be the length of the longest path if I draw the proof out like a DAG. So here the depth would be 4, I guess. 1, 2, 3, 4. The width of a proof is the size of the largest clause that appears in it. So here it would be 3 because we have this clause right here that has size 3. And I'll say it's a tree-like proof if any derived clause gets used at most points. Okay, so this is a proof with 10 clauses. It has width 3, depth 4. It's not a tree-like proof because this clause that's derived got used more than once. So, but I could always turn it into a tree-like proof. How? Well, just take whatever clause that was used more than once and then just derive it twice and then just recursively split. This will cause an exponential blow up in the proof size, but whatever, I can still do the conversion. Does that make sense? Okay, good. This is all review, I'm sure. So let's talk about how do we actually automate resolution? Well, let's first start with, for lack of a better name, I'm going to call the dumb algorithm. And that's the following. I've already said it in words earlier. So as input, I get my CNF formula. And then for S, that just goes on forever. And for every binary string of length S, I'm just going to check if this string encodes a resolution refutation of F. And if so, I'll return it. Does that make sense? This thing's not even guaranteed to halt. I'm going to assume this thing's unsatisfiable. Let's not worry about that kind of detail. Okay. But this is an algorithm. If you give me an unsatisfiable thing, it's complete. It's certainly an automating algorithm, right? Like given any tautology, it'll output a resolution proof of it. And this is in some sense, the obvious brute force algorithm. This works for any proof system at all, right? I can just, as long as I can test that something is a proof, which is a requirement for a proof system, I can write down this algorithm for it. And what's the runtime of it? Well, if you work it out, it runs in time. I mean, this is an exponential time loop in the thing, so it's totally dominated by the largest S. So we're going to get something like order S, the size of the shortest proof times 2 to the size of the shortest proof, which is, I'll just be lazy and write it like this, 2 to the order of the length of the shortest proof. That makes sense? So basically what this is doing is it's just brute forcing over all proofs until I find one. Okay, so that's great. In the sense that it's very simple to analyze this algorithm. It does verify that we have some kind of slow thing, but can we do better? The way that we can do better is by using the following observation. So instead of just looking at the length of the proof, we're going to instead look at the width of the largest clause inside the proof. So here's a really obvious observation, I guess. If I have n variables and I count up the number of clauses of width at most w, well, how many are there? Well, there's going to be something like n to the order w, right? A proof of this is right here. I mean, the number of width w clauses is exactly this expression right here. Right? I choose I literals to go in I choose I variables to go in my clause, and I have to give them all signs. That's 2 to the I times n choose I. Okay, good. Well, then when I know this, you can now define this width automating algorithm. Okay, and what this algorithm is going to do is it's going to return, if a proof exists, it's going to return a proof where every clause has width at most w. Okay, so how does this work? Well, I get my formula and I get some parameter w as the input. And then I start with my proof by throwing in all the axioms. And then as long as I haven't finished, like I haven't derived a contradiction, or until maybe the proof doesn't change, like I can't derive anything new, I'll just do the following. For every single pair, just resolve them together if I can, and then append it to the proof if the new clause is low width. Does that make sense? Very simple proof. And then once the bottom it returns, and once the empty clause appears in my proof, I'll return it. Otherwise, I'll fail because then there is no width w proof. Yeah.
No, return L, what's L?
Oh, that's a typo. That should be pi. Sorry. Thank you. Okay, good. So what's nice about this proof is that it actually runs in much better time, right? If there is a constant width resolution refutation, right, then this is going to output that constant width refutation in polynomial time, right? If there's a refutation of width 7 of my formula, well, then this is going to output it at least in time n to the 7, which is much, much better than just brute forcing over all of this. Yeah.
You're eliminating the original clauses from this width computation, right?
No, I'm counting them. Yeah, that's a subtle point. Yeah. So if my original guy, if these guys have big width, then I need to count that. Yeah, you do need to count that. You can always do like a Satan transformation and blast it down to 3CNF or something. Yeah. So yeah, so this algorithm runs in time n to the w. It outputs a width w clause of a width w refutation if one exists. But I'm going to note here that low width refutations might not always exist, right? So it's not an easy fact, but it turns out that there are constant width CNF formulas that require basically linear width to refute. Like you more or less have to look at every single variable in your formula in order to refute it. Okay. So what this says is that if I wanted to run this algorithm up to w equals 0, 1, all the way up, this tells you that maybe you have to go all the way up to n, right? However, it turns out that you don't actually always have to go all the way up to n. You can actually do slightly better than that. And that follows from this beautiful size-width relationship due to Benteson-Vigerson, which I've stated here. And it says the following. If you give me any unsatisfiable CNF formula on n variables, well, then the width it's going to take to refute that formula is bounded by roughly square root n times the log of the size of refuting that formula. Okay. So this is quite interesting, right? Because if I have what this is telling you is that if I have a polynomial size proof, say like something like n to the constant here, well, that's going to turn into square root n. It suffices to look only up to width square root n. And this tells you immediately, just by running this algorithm that we just saw, that you can automate resolution in a highly non-trivial runtime, much, much better than just this 2 to the s that we saw. Now we're getting something like 2 to the square root n log s, with some log n factors being kind of suppressed here. Does that make sense? So I'm not going to prove this theorem, but I will point out that this is a really highly non-trivial thing. Like this really does improve on the dumb brute force algorithm for resolution. Like this is always going to do better than a brute force algorithm for resolution. Now the downside, of course, is that it is a sub-exponential time algorithm, right? Like it's still running in something like exponential in n, weakly exponential in n, but it is doing much better. It is handily sort of beating this brute force algorithm that we were looking at. Does that make sense? Okay, cool. Well, I said earlier that.
Sorry, can you go back one
Oh yeah, sure.
This is true only if you have a polynomial size proof. No?
Yeah, it's parameterized by the proof size here. So it doesn't matter if I have an exponential size proof, then this will just collapse to 2 to the n. Yeah. Which will be, everything will just sort of, the numbers will just sort of work out.
Robert?
Yeah.
Is it also the case that they're solving different problems? Like the dumb algorithm is finding the smallest proof?
Yeah, I'll get back to that.
Oh, okay, good.
Yeah. You're right, I'll get back to that. Yeah. This is automating it though. It is outputting a proof each time. Yeah. Okay, cool. So let's move on to tree-like resolution. So I said a second ago that we had this kind of ad hoc algorithm that sort of does better for tree-like resolution. It actually gets the right. Well, let's first think about it. This algorithm that we just showed you, this does not automate tree-like resolution. So why is that? All right.
Tree resolution can have arbitrary width.
You could bound the width of a tree resolution proof, actually. There's nothing special about it. Yeah, you could consider bounded with tree resolution.
I know, but the standard tree resolution.
That's true. Yeah. But I could always run it for width 1, 2, you know what I mean? Just like I just did. That's not quite the answer.
You're producing tree-like proofs.
Exactly. The algorithm is not going to produce a tree-like proof, right? It will produce a proof, but it might produce a DAG-like proof. And if you look at this width algorithm, it's certainly going to be doing DAG-like deduction steps, right? Like I'm really not putting any control over what I'm doing here. I'm just blindly resolving things together as long as I can. So it's probably going to be a big mess, very highly DAG-like. Be very far from a tree-like proof, right? So this algorithm does not automate tree-like resolution. And it's really important to keep these things in mind that you might think that automatability is somehow monotone, right? Like if a system gets stronger, maybe I can maybe an automating algorithm will somehow work its way back down, but this is not true, right? We have to be careful about these kinds of things. But it does turn out that you can actually automate tree-like resolution. This was due to Dean Patassi in '96. And the runtime that they get is actually much better than the runtime that you got for the automating algorithm for resolution. It's actually just n to the log s. We've just eliminated this n in the exponent completely. This is a quasi-polynomial time automating algorithm. So how do we compare this with the thing that we just seen? Well, on the one hand, this is much faster than just automating resolution, right? But on the other hand, tree-like proofs can be much larger than DAG-like resolution proofs. Like there's exponential separations between the two. And it's very important that in this exponent, we get like an, the exponent is in the size of the smallest tree resolution proof and not in terms of the size of the smallest resolution proof. Does that make sense? Okay, cool. Well, how does this algorithm work? Well, I can sketch it for you. So here's my tree-like resolution proof. So it starts with some formula F, and we have my proof is P, and say it's eventually deduces the empty clause. So how can we find this proof? Well, the idea is the following. We're going to look at the last resolution step that occurred in the proof. Okay, so it resolved on some variable x sub I. which means we can now split the proof into two totally distinct subproofs, pi L and pi sub R. And because the graph of the proof is a tree, we know that at least one of these two pieces is going to have at most half of the proof length. Now, this is great because as soon as you've dropped the size of anything by a constant factor, you should start thinking recursion, right? And that's exactly where the log s and the exponent is going to turn up in. Okay. So what are we going to do? Well, if I look at these two subproofs, what you could do is you can restrict xi on this side to be false, and you can restrict xi on this side to be true. And now I get two little refutations of the restricted formula. F restricted by xi is 0 and f restricted to xi is 1, right? So now if I can recursively solve these two subproblems, I can patch them. The idea is to patch them back together. And it turns out that this is possible. If I have a refutation of a restricted formula, well, I can just take that same sequence of resolutions and weakenings that happened, and on the original formula, it'll just give me a proof of x of I. Does that make sense? So this means, okay, if I have a tree refutation of size at most s, will I get a tree refutation of one of these two subproblems of size at most s? So now I have my recursion all set up. What am I going to do? For every literal in the formula, I'm just going to set that literal to false and to true. Okay, and I'll recurse on these two subproblems, and I'll do them in parallel. I know that on one of the sides, the size of it is going to drop by at least half, right? On the other side, the size of the proof might not drop, but I do know that the number of variables decreased by 1 because I fixed it, right? So on both sides, we're making some progress. And then once I've solved these two subproblems, I can just use my fact and recombine them back into a proof of the original thing. Okay, good. So this, you plug this in, you figure out what the recurrence relation is for the runtime, and you solve it, and it turns out to be something like n to the log s. Okay, the dominating step here is really, at least on one side we divide by 2 every time, so it's going to be log s stages, and we have to do like order n choices, order n branches at the top. So it should be something like n to the log s. Hopefully that's believable. Does that make sense? Okay. And hopefully you can see, like here, we're really taking advantage of the tree-like structure. We're using the fact that the proof on one side and the proof on the other side really don't talk to each other, right? I can really just sort of shove those off, solve them completely independently, and then recombine them. This kind of argument really doesn't work for the DAG-like setting. Is there any questions about that? Okay, great. So let's move on to talking about some of these algebraic systems that Albert mentioned in his talk. I'm not going to go into great detail because I don't want to spend the time to sort of define them and things like that. But let me just say that these algebraic systems, they also admit a form of this width automatability that we saw a second ago. So the proof systems for these algebraic proof systems, they're composed of algebraic expressions, so polynomial identities or inequalities. And it turns out that you can find degree D proofs in these systems in time roughly n to the D. Just like in resolution, you could find width W proofs in time roughly n to the W. But you need more sophisticated techniques than just brute forcing up to something, because I'm dealing with a richer set of lines in my proofs, right? So throw up a table of what you can kind of do in order to get these things. So say for, you can use things like Gaussian elimination for Null-Stellensatz. For polynomial calculus, you need something like Robere bases. And then for these semi-algebraic systems, you need linear or semi-definite programming, with a little caveat that you need to watch the sizes of the coefficients here. But let me just say that it turns out that you can still do degree automatability under some mild assumptions in all of these systems for CNF formulas. And this is nice because these weak algebraic systems, with the exception of Null-Stellensatz, but I'll mention that in a second, also satisfy this size degree relation, just like resolution does, right? So if I take polynomial calculus or Charlie-Adams or sums of squares, again, with a little bit of a coefficient size caveat for these things, but let's not worry about it. The lowest degree proof of these systems is going to have exactly the same expression in the exponent as with resolution, something like square root n times log of the proof size. Does that make sense? So as a corollary, we can do the exact same thing. We can automate these systems also in time roughly n to the square root n log s. that make sense? And now I've only named 3 systems here, so you might be worrying about Null-Stellan sets. My understanding is that, I didn't actually know this, but I learned this like a week ago, that apparently you can modify the tree-like resolution proof to get the same bound. So Null-Stellan sets does not satisfy this relation, provably does not satisfy this relation, but it turns out there's an alternate method to get the same upper bound in the proof for Null-Stellan sets. But let's just sweep that aside for a second. Okay, cool. And that, for upper bounds, is actually all we essentially know. For all of these stronger proof systems, we really do not know anything positive for automatability beyond this stupid brute force algorithm where you just blast out all the bits and just verify that it is actually a proof of the right type. And I think it's an excellent problem to try and understand, can you, for these stronger proof systems, can you even get something that slightly beats brute force search? Like it's really not obvious to me that you can do that, but for resolution you can. Like what's the difference? We know the proofs can be much shorter, and all I'm asking for you to do is beat 2 to the s, right? Like just by a little bit. This is a really nice problem somehow. Okay, any questions about that? The upper bound section. Yeah, last one.
If you use extension variables on res k, res log n, what can you get in the end? Like you do for res k, you add n to the k variables that represents conjunction, and then you run resolution.
Oh yeah, that's a good question actually. It'll be high width is the issue, but you might get something like that. Yeah, because you have unbounded fan and ors, but something you can say.
Robert, I forget to tell you, but you should also repeat the question because there are some people attending.
Sorry, thank you.
Yeah, sorry for not mentioning this before.
Yeah, so the question was for res k, which is like intuitively a proof system where the lines are ors of low width ands. Maybe you could just reduce to the resolution automatability by just replacing every and by a variable and just then running the algorithm we just saw. I'm worried about the width of the or at the top, but maybe there's something you could do that. Yeah.
Your upper bound algorithms haven't used randomization.
That's true. Everything is deterministic. For randomization, as far as we know, it doesn't help for certifying a proof. For satisfiability, it seems to
I'm
certainly
trying
help.
to talk to you about this afterward because it might be a bug in my book, but I think my book refers to a randomized algorithm that will find a short proof if it exists.
Oh, okay. Well, I'd love to hear about it then. Yeah. Any other questions? Oh, yeah, you're done.
You said that better than brute force algorithms would be nice. Are there like better algorithms to lower bound connections from better than brute force for some?
Great question. Yeah, none that I know of. Totally unexplored. Like, not that it doesn't exist, but just totally unexplored.
What was the question?
So Nishan's question, Nishan's question was are there like, could you somehow take the lack of better than brute force algorithms and maybe convert them into something? Like maybe if I can beat brute force even slightly for extended frega, maybe some other surprising connection, maybe some other surprising result would follow. And I don't know of any such connection. Okay. All right, so let's move on to the lower bound portion, which is the part where all the SAT people go. It's just my experience from talking to SAT people. Okay, cool. What?
We're all SAT.
We're all SAT people here. Okay, yeah. And the whole audience went. Okay, great. Okay, so let's forget about the detailed thing and let's just think about the sort of rough separation between crypto P versus NP. So let's first talk about how we can use crypto to rule out weak automatability. Okay. And I'm actually gonna pretty much just completely prove this modulo some pretty significant hand waves. But it's that's yeah, you can take that thing. So how do these proof systems work? Well, how do these results work? Sorry. So the basic idea is the following. So I'm going to informally define a cryptographic object. It's called a one-way permutation. And a one-way permutation is just a family of functions. Each of them is a permutation. Like each of them permutes, say, the strings of length n. And they're polynomial time computable, but they're hard to invert. So I mean that if you give me some string in the image, it's going to be hard for me to find something in the pre-image on average. It turns out that if this is true, it's hard to even predict some bit in the pre-image on average. Okay. This is a pretty standard cryptographic assumption that these things exist. I'll say that this is stronger than necessary. You don't really need an assumption this strong, but this is just going to simplify the presentation a little bit. And the whole idea of doing this goes back to a paper by Krychek and Pudlock, which shows that if we can weakly automate these strong proof systems, well, then we can actually use this automation algorithm to somehow invert a one-way permutation. Okay. So Krychek and Pudlock sort of did this for extended Frege, although they did it mostly in the language of bounded arithmetic. For weaker proof systems like TC0 Frege and AC0 Frege and Frege, this was sort of done by Bonnet, Patassi, and Raz. And the keyword here is feasible. Is something called feasible interpolation, which if you've been to proof complexity talks before, you've probably seen it, but don't even worry about it. I'm just going to do, you can kind of forget that I even put that word there. So how does this work? How do we take an automating algorithm and use it to break a cryptographic primitive? Well, the idea is the following. If I have a one-way permutation, well, I'm going to define the following two formulas. The first formula has variables x and z, and it's going to say the following. Well, if I evaluate x, the permutation on x, I get z, and also the ith bit is 0. Okay. And this other formula says, well, if I evaluate y and I get z, and the ith bit is actually 1. Does that make sense? So the conjunction of these things is unsatisfiable, right? Well, I mean, why is this unsatisfiable? Well, I'm saying that two things map to z, but they have opposite bits, and it's a permutation, right? There's only one thing that maps to z, right? So this is an unsatisfiable formula. And moreover, since it's a permutation, we actually know that for every single z I can plug in here, exactly one of these two things is satisfiable, right? Well, at most one maybe, but yeah. Does that make sense? Okay, so now here's the claim.
I have a question. What
Yeah.
Xi is?
Huh? Sorry? What was the question?
I is fixed or
I is fixed here. Yeah. We can do this for any I.
Okay.
Yeah. X1. Yeah, say X1, but it's important that we'll pick it for any I in the actual proof, but let's just, yeah. You can say X1 if you want. So now here's the claim. If I have some proof system, which is nice, and I'll say what nice means in a second, very, very mild properties on the proofs. It's automatable, and there's a short refutation of this function formula here that basically just says that the permutation is indeed a function, like it has an output, right? Then you can actually take that automating algorithm and invert the permutation. So what does nice mean? Well, nice just means that if I have a short refutation of f, then I can extract either a short refutation of this left-hand side or of this right-hand side after I plug in some of these z variables. Okay. And now here's a sketch of the proof of how we actually see this. Well, I want to invert this function n. So I'm given some output, some assignment to the z variables, and I want to predict, say, the ith bit of the input. Okay. So how am I going to do it? Well, since the proof is nice, since the proof system is nice, and since I have a short proof of f, I can just run the automating algorithm on ax of alpha for, say, polynomially many steps, right? After I've done this, if the algorithm hasn't halted at this point, well, because there is a short proof of ax of alpha, that means that there's no proof of ax of alpha. And so therefore it must be satisfiable because it was a permutation to begin with. And on the other hand, if it did halt, then this is unsatisfiable, right? And so in this case, I could just run it on the B side, and I know that the B side is actually going to be satisfiable because the whole thing is unsatisfiable. So if A is unsat, then the other one has to be satisfiable. So I've turned this automating algorithm into a satisfiability test, whether or not A or B is satisfiable. But now just by looking at the structure of these formulas, if I know which one of these is satisfiable, I'm now able to predict what the ith input bit is given an output of this alpha, right? And that's enough to break the one-way permutation. Turns out that you can, just by predicting what's called the hardcore bit, you can just turn this into, you can eventually turn this into a prediction of actually a full inversion. Okay. This is a nice argument. It's relatively simple. It fits on one slide, pretty much. So positives, negatives. Well, the good thing about these sort of crypto type arguments is that they have a very, very strong conclusion, right? They even rule out weak automatability. All I need is an algorithm that just outputs a proof that A is unsatisfiable that I can verify, right? And moreover, if you look at the strength of your cryptography assumption, you can even like bound the runtime of the algorithm, right? Like you can see there's a very tight connection between the automating runtime of the algorithm and the runtime of inverting the permutation, right? Like the algorithm is so simple, it's very easy to extract even quite tight runtime bounds from this kinds of arguments. The downside of this is that we need extremely strong assumptions, right? We believe that P is different from NP, and we're happy to assume it. We believe that cryptography holds, and we're happy to assume it. But I mean, at some point, you know, when the systems start getting quite weak, you start getting into the realm of cryptography assumptions that are so strong that maybe we believe them, but we should maybe hold back a little bit. So like, you know, for these weak proof systems like AC0 Frege, you need to know not only is it hard to factor numbers, you need to factor numbers of a certain type. And moreover, it has to be very, very hard to factor them. Like we shouldn't even expect like an exponential, like a sub-exponential time algorithm that can factor them. So this is kind of unfortunate. And the reason why this only works for these strong proof systems is because we need to be able to intuitively reason about cryptographic constructions inside the proof systems itself, right? In order to do this argument, the proof system needs to be able to refute this formula, which is basically encoding if a cryptographic function, you know, works. And resolution, we should probably suspect, can't reason about. If I give you a circuit that, you know, I mean, we shouldn't expect resolution to be able to reason that this circuit is actually computing a one-way permutation, right? So this is, roughly speaking, what we have for these very strong proof systems. Are there any questions about this so far? Yeah,
can you go back to the slide where you, so you have some quote unquote nice properties.
Yeah.
So the one question is, what are they?
Oh, it's right here. It's just right here. Yeah. Oh, sorry. It just says if I have a short refutation of this F, then I get either, then I can get from that either there's a short refutation of just one side, A, or the other side, B, after I plug in something for the Z variables. Yeah. This is basically, you can think of it as being like closure under restrictions. If I have a proof of a formula and I plug in some variables, then I get a proof of the restricted formula.
So the contrapositive of this would be the function is believed to be not invertible.
Yeah.
And one of these properties should not hold.
Exactly right. Yeah.
So it doesn't immediately give you the contrapositive doesn't immediately say non-automatability.
No, that's true. But extended Frege, for instance, is nice.
Yeah.
And also has short refutations of F. Yeah. This is true. This is where all the work is, in fact. You have to actually prove inside the proof systems that you can refute these Fs. Yeah. Thank you. Yeah. Thanks for clarifying. That's exactly it. Yeah. Okay. So I got 10 minutes left. So I'll kind of, I'm good. I should have enough time. So let's talk about this lower side stuff, the P not equal NP, and from the automatability from P versus NP. And for this, I want to go back to one of my first slides, which was talking about the decision problem, right? So we saw earlier that NP completeness of this just decision problem doesn't imply that automatability is hard, because we're looking for, we need something stronger. We need to say, not only is it hard to tell the difference between K versus K plus 1, we need to tell the difference off like a polynomial factor approximation in the proof length, right? And all of these NP completeness results from the 90s, if you go in and look at them, what they actually get is something like a sublinear factor off, very slightly sublinear factor off from approximating the minimum proof length, right? So this gives you something in terms of non-automatability. It says, okay, you can't be off by, say, a linear factor. Maybe that's hard. But a polynomial factor, which is much more reasonable, is out of reach from these sorts of things. And something that I want to emphasize here is that all of these results that come from NP hardness, they're studying the hardness not of automatability, but of the hardness of approximating this proof length, right? This is where all of the hardness is coming from. It's not coming from the actual finding of the proof itself. It's just coming from approximating the proof length being hard. Okay. Let's again talk about resolution. And I'll emphasize again that all these results show that even just approximating the shortest resolution proof is hard. So in the 90s, a sequence of works showed that up to an additive polynomial factor, it's hard to prove resolution. This is just what you get out of the NP completeness proof if you look at it very carefully. Not only is it k versus k plus 1, it's actually k versus maybe k plus a polynomial. Even that is hard to distinguish unless p equals np. The follow-up paper by Aleknovich, Busmaran, and Potassi showed that this like slightly sublinear factor is hard unless p equals np. And then there was this breakthrough paper by Aleknovich and Razbarov who showed polynomial inapproximability is hard, but unfortunately not on p versus np, but on a assumption from parameterized complexity, which I won't tell you, but is a complexity theoretic assumption. So this was, of course, improved just a couple of years ago by Atsarius and Mueller, who updated this parameterized complexity assumption into actual p versus np. And the nice thing about the Atsarius-Mueller proof is that it sort of relaxes smoothly. If you want to approximate within a quasi-polynomial factor, well, then that'll imply that np is in quasi-polynomial time. If you want to approximate the proof length within a sub-exponential factor, well, then that'll tell you that NP is in sub-exponential time. So it's actually kind of a smooth transition here. Does that make sense? So I'm not going to go into too much of the details of this Atsarius-Mueller proof, but I will tell you just a little bit about it. Okay, I'll tell you why this was hard to do. I think, in my opinion, why it was hard to do, and why even just kind of thinking about it is weird. So our goal here is to show that approximating resolution proof length implies that p equals np. If I have some algorithm that can just approximate proof length, then p equals np. And so, well, I'm giving an NP completeness reduction, so I got to give a reduction from SAT, right? I'll start from SAT and I'll reduce it to this approximating proof length problem, right? But now the question is what can such a reduction look like, right? Well, it's going to look something like this. It gets a formula. I don't know if it's satisfiable or not. If it is satisfiable, then it's going to have the resulting formula has to have a short resolution proof. If it's unsatisfiable, then it must have no short resolution proof, right? I haven't told you anything yet. This is basically content free if you know the definition of a reduction, right? But I want to point out that this is a very weird thing to believe should exist. How could we come up with such a thing? So here's a first option, which I think is kind of obvious if you just think about it for 5 minutes, right? Well, if f is satisfiable, I'll output some formula that has a short resolution proof. And if f is unsatisfiable, well, then I'll just output a satisfiable formula. That has no short resolution proof, right? This is one obvious reduction to do. Does that make sense? Now, what's the problem with this reduction?
Seems like a great setup.
Exactly. Yeah. The problem with this reduction is that now I can detect if a formula is satisfiable or not and flip the answer for it, right? So if I had such a reduction, then you'd get that NP equals co-NP like automatically, just for free. So this just is not going to work, right? So now the second option, which was the one followed by these earlier papers, was the following. If f was satisfiable, well, then we'll do the same thing. We'll say it's unsatisfiable and has a short resolution proof. And now if it's unsatisfiable, I'm going to again output an unsatisfiable formula, but I'm going to make it require a long resolution proof now, right? And the output is, in this case, the output is always going to be unsatisfiable, right? And the difference is that we want as big a gap as possible between what short and long is here, right? But now we're in a very weird kind of space because I'm given a formula f, and I don't know if it's satisfiable or not. And I need to always output an unsatisfiable formula. How would you come up with such a thing? Like, it's just a very these reductions that did this are very intricate. Like, in order to come up with these types of reductions, they're very, very strange. You have to somehow convert any formula into an unsatisfiable formula, right? Oh, yeah. Yeah, that's true. Yeah. Yeah, it's not even from SAT, really. Yeah, they actually didn't even use SAT. They used a different form. They used a different thing completely. Okay, so what actually happened? Well, here's the Atzerius-Müller proof. Well, on the one hand, same thing. If F is satisfiable, we'll output a short proof. And then in the second case, they're going to output a formula. Sometimes this formula will be satisfiable, and in this case, it will have no short proof. Sometimes it will be unsatisfiable and require long proofs. And so it was really this kind of spreading the hardness across these two things in this choice of reduction that I think really made this possible. So what is this R of F? Well, it's actually quite simple. I'll just tell you the definition of the reduction, and then I'll skip ahead. Well, it does the following. If I'm given a CNF formula and some S, I'm going to define the following propositional formula. And the formula is kind of a meta formula. It's going to say, well, this thing has a short proof in resolution. And my reduction is then going to take F, and it's going to output ref of F and say polynomial size. So somehow non-automatability is being inherited from the hardness of proving resolution lower bounds. And this was kind of the key thing. So if we think about how this would work, well, if F was satisfiable, then this ref formula is going to be unsatisfiable. And in fact, it has a short resolution refutation, right? If F is satisfiable, then there's no resolution refutation at all. So this formula is unsat. And if F is unsat, well, then either it has a short proof, and so it's satisfiable, or it has no short proof, and then we need to actually prove that it requires a long refutation. And that is where all the work is. Although a significant amount of the cleverness came from just thinking to use this formula in the first place. I think once you have the formula, the lower bound itself is not so bad somehow. Okay, cool. So after this Atzerius-Müller paper, well, we were able to sort of generalize this to sort of all of these other proof systems here. So all of these other arguments, they're basically using variants of this ref formula. So there's nothing really, well, there's new ideas that have to go into each of these different cases, but I mean, the core of it is really using the idea of using this ref formula. That was really the new idea that sort of led to this breakthrough in all these non-automatability results here. Okay, so in my last couple minutes, I'm going to talk a little bit about the future, and I'll go quick because I know I'm getting quite low on time. And I want to outline just like three obvious directions to me, at least. So the first direction, which I think is completely obvious, is to complete this picture here. We have these annoying sandwich proof systems where we don't really know if they're automatable or not. Surely they're not automatable. For Schiraldi atoms and sum of squares, this is something that we've been thinking about quite a bit, and hopefully we'll have something interesting to say soon. For res log n, it seems like you kind of need new ideas completely. Proving interesting lower bounds for res log n is like a sort of a well-known open problem in proof complexity itself. So this seems like hard, and this seems like if you could make progress on this, you'd make progress on other things as well. Another obvious thing to do is in these results, we know that under P not equal NP, we can deduce that there's no automatability. And under crypto, we can assume there's no weak automatability. Can we somehow flip these, right? Can I somehow use stronger assumptions to deduce weak automatability results down here, right? We don't know anything about whether or not these weak proof systems can be weakly automated. Maybe it can be, right? And on the other side, maybe under weaker assumptions up here, we can actually prove that these things are simply not automatable. This, of course, is going to require totally different techniques because we don't know how to prove lower bounds for these systems. For AC0 Frege, it's conceivable that you could make this strategy work. The second direction is one that I mentioned right at the beginning of the talk, which I think is nice. And that is, can you give anything non-trivial about upper bounds for these strong proof systems, like anything at all, anything even slightly sub-exponential? I think that would be interesting. I think that would be super interesting because it would somehow say that at least once the proof systems are very, very strong, you can actually harness that somehow. Even a little tiny bit would be super interesting complexity theoretically. Or we could bring up what Newton mentioned earlier, and that is maybe the non-existence of non-trivial algorithms up here could imply something interesting in a complexity theoretic sense. That's another very interesting direction. And the last thing that I want to isolate is what Susanna mentioned at the very beginning of the talk. And this was really her idea. I'm giving her completely the credit for this idea, which is the problem of like finding short proofs. Okay. So let's go back and think about this dumb algorithm again for a second. This algorithm ran in exponential time, 2 to the s. But what was very interesting about it and was different about all the other algorithms that we saw is that it always outputs the shortest proof, right? The other algorithms, they might output a longer proof. There's nothing stopping them from outputting a much longer proof, like an exponentially sized proof. This algorithm right here is always going to output the shortest one, no matter what. However, it runs in time 2 to the s, right? Well, if you want to find the shortest proof, the question is this actually necessary, right? Or can we somehow slightly beat the sub-exponential time even for finding just the shortest proof itself? It's a very natural question, I think. Both answers would be interesting in my opinion. If a positive result would be super interesting, and a negative result would actually be super duper interesting. I'm a lower bounds person, so it would be super interesting for me, because then you would get something like a super exponential lower bound in the runtime here, which would be just totally cool, I think. And I'm willing to make a conjecture. So for every here's a conjecture that I'm going to make. For every sufficiently strong proof system, let's say it can P simulate resolution, because tree-like resolution kind of would break this. Any algorithm that outputs the actual shortest P proof must take this time, must take at least 2 to the s time. Seems like a totally reasonable conjecture. I don't see how you can do anything better than just this dumb brute force algorithm. And proving this conjecture conditioned on a normal complexity theoretic assumption, like say strong exponential time hypothesis or something like that, I think is a fascinating problem. And yeah, that's all I have to say. So thanks for listening.
Let's take 1 or 2 questions while the next speaker sets up.
I have a question on your talk. The first time it's ever happened.
Okay, maybe a dumb question, but it seems like for your dumb algorithm, you can make it a little smarter by just doing some kind of well-formedness checks or using a grammar or something, but that doesn't improve your...
That wouldn't improve the exponent by much, right? Yeah, the question would be to like change the 2 to the s to something asymptotically smaller than s in the exponent. You can certainly improve, you can certainly improve this order s in the front, yeah, by doing these kinds of tricks.
We still have time for questions while the next speaker is setting up. So here's a very ill-posed question. So proving that proof search is NP hard is like, well, the original problem was also NP hard, SAT, and still we have SAT solvers solving them. So like, is it possible to get like a practical theory of non-automatability? Like it could, because it could be just as SAT is somehow easy a lot of the time. Maybe proof search is also
that's
like
another
automatability. Maybe also that's easy in practice.
That's another great question. Like some kind of average case extension of the theory of automatability is a great question. Like if I assume some sort of distribution on the tautologies that I get, maybe then you can do better on average than on finding. Like certainly we know that many formulas are easy for resolution. So if I have a distribution of easy formulas, can I always find them, right? Like you can there's lots of, this is something that has been completely unexplored as far as I know. Like, and I think that that's a great open problem, and is quite tied to this sort of one of the driving questions of understanding SAT solvers, which is like, why are instances easy and why are instances hard, right? In practice, we really don't know that.
So let's thank the speaker again in the hope that the slides for the next speaker will be up